Hi everyone. In this video we're going to talk about Rolle's theorem and the mean value theorem, which actually provides the bedrock for the fundamental theorem of calculus, which we'll see in Calculus 2. So let's begin by talking about Rolle's theorem with a nice easy picture. Yeah? So suppose we have our favorite function, and let's say it looks something like this. Yeah? I don't know if my picture is okay. Yeah, it looks okay. But our function needs to begin and end at the same spot. Okay? And let's suppose we have the following conditions. Suppose the function that I'm about to draw is continuous on the closed bounded interval between a and b. Yeah? So it's continuous on the closed bounded interval, and it's differentiable. Diffable is differentiable, remember, on the open interval a to b. Yeah? And we need to assume that the function begins and it ends at the same y value. Okay? So it begins and ends at the same y value. So, and we'll see an example where you could be, we need continuity on the closed, but you won't necessarily be differentiable on the closed interval. So we'll see an example of that, I promise. But suppose we draw a function that's continuous on the closed bounded interval a, b, and it's differentiable on the open interval a, b, and the function begins and ends at whatever the y value is. So let's draw such a function. So maybe it looks something like this, right? Nice and smooth. There it is. So what Rolle's theorem says is that, well, what must happen somewhere between a and b? We must have at least one point, and indeed in this picture there are, it looks like 3 points, where we have horizontal tangent lines. So the conclusion of Rolle's theorem says that there is at least one value c in the open interval between a and b such that f prime of c is equal to 0. Yeah? And this is called Rolle's theorem, or Rolle's theorem if you like pronouncing the E. All right. So what's a case where why can't we have differentiability on the closed interval? In this picture I tried to show an example where we might not have differentiability on the closed interval, because maybe you have a vertical tangent at an endpoint or something, and that doesn't really affect the conclusion. As long as we're nice and continuous on the closed interval, including the endpoints, and smooth in between with no vertical tangents, right, then we're guaranteed to have at least one point at which the tangent line is horizontal. So let's talk about, let's just talk through the proof together, and we can discuss this more in office hours if you're interested. Yeah. But let's just give a sketch of the proof. Since we know that f of x, oops, got that too high there, is continuous on the closed interval ab, yeah, because we have continuity, what do we know by one of our recent videos? We know that by the extreme value theorem, right? The extreme value theorem has to apply. By the extreme value theorem, it has a max and a min. Yeah? So there are two cases that we need to consider with Rolle's theorem. If the max and the min are at the endpoints, so if the endpoints are both the maximum and the minimum values, what does that mean? Well, they have to be the same by Rolle's theorem, right? Rolle's theorem, you have to begin and end at the same y value. So if the max and min are at the same y value, what must the function be? It has to be a constant function. And what do we know about some point in between a and b on a constant function? The derivative of 0, right? The next case for Rolle's theorem, suppose that one of the max or the mins is not at an endpoint, yeah? So it has to occur somewhere between a and b, yeah? So suppose it looks something like this, yeah? So what does this mean for us? Well, we know that by the extreme value theorem, it attains a maximum and a minimum. Yeah? So suppose it attains this minimum somewhere, maybe it's the point C at which it attains its minimum value. And what do we know? One of our observations in the previous video is that the point at which we attain a minimum, the derivative must either be 0 or does not exist, right? But what's our assumption strictly between A and B? We must have differentiability. So what's the only choice? We must have that the derivative is 0. Yeah? And that's kind of the verbal reasoning for why Rolle's theorem is true. So let's do an example. Okay? All right. Example. Does your favorite function f of x equal 2x times the square root of x plus 1 satisfy the assumptions of Rolle's theorem? Yeah? So what were the assumptions that we need? We need assumption 1. F must be continuous on the closed interval. I need to give you a closed interval. Let's go with -1 to 0. Sorry about that. Yeah. So we need to check to see if f is continuous on the closed interval -1 to 0. It needs to be differentiable on the open interval from -1 to 0. And f of -1 has to equal to f of 0. So pause the video, go through these 3 conditions and see if this function satisfies each one. All right, so the function is definitely continuous between -1 and 0. We know that the domain, yeah, is certainly going to be from -1 to infinity, and so -1 is included, and we don't have any problems with continuity if you take limits as you approach -1 from the right. So you might want to go back and review what it means to be continuous on a closed interval. The limit is totally fine everywhere on the interior, and as we approach -1, we have to approach it from the right. The limit's going to be okay. And what's the limit as we approach 0 from the left? That one's going to be okay as well. Are we differentiable from -1 to 0? Well, let's see. Yeah. Let's compute f prime. F prime of x, we need to do the product rule here. So that's the first times the derivative of the second. Plus the second times the derivative of the first. Yeah. Is this function nice and defined strictly between -1 and 0? Yeah, because our only problem point would be at x equals -1, so we'd have to throw that one out. Turns out this is one of the cases where we do have a vertical tangent. So we are differentiable on the open interval here. And do we satisfy f of -1 equals f of 0? F of -1 is 0. F of 0 is also 0. So this is also true. So we see check, check, check. We definitely satisfy the assumptions of Rolle's theorem. So what does that mean? There is a point between -1 and 0 at which we have a horizontal tangent line. How do we find it? Let's find the point guaranteed by the theorem. How do we do that? We just set this equal to 0. Yeah? And we've seen this type of thing before. How do we solve this equation? We factor out the term with the largest negative exponent. So we factor out x plus 1 to the -1/2 power. And what's left over? I see x plus 2 times x plus 1. Yeah? I know that this first term can never be 0. And where does this term equal 0? Precisely whenever x is equal to -2/3. Yeah? And 2/3 indeed does live between -1 and 0. All right, let's do another example. Let f of x be a twice differentiable function. And suppose I give you the following table of values for f of x and f prime of x. Suppose our x values are 1, 2, and 3 that I give you. F of x is 0, 5, 3. F prime of x is 1, 1, 4. Yeah? So, two questions here. The first question is the following. Must f of x have a horizontal tangent on the interval 1 to 3? Yeah? Pause the video, see what you think. Alright, so first, it helps in these types of problems with tables to plot the points, yeah? So here's 1, 2, 3. F of 1 is 0, f of 2 looks like 5, f of 3 is 3. Yeah? We have literally no idea what happens in between these points, but I know it's a nice differentiable function. So let me draw a nice, smooth, possibly wiggly function, right? Who knows what's happening, right? We don't really know, but it looks something maybe like this, right? Must we have a horizontal tangent? Well, the curve that I drew certainly does. Yeah? Why must we have one, though? How can we prove that we do? Well, what do we know has to happen between 0 and 5? Well, because f of x is differentiable, it's continuous, right? So what value must it cross somewhere between 0 and 5? It must cross 3 by the intermediate value theorem. So we know that there is some c in the interval between 1 and 3, such that, and I know that the endpoints won't be there because they're not, such that f of c is equal to 3. Yeah? So I know that f of this point c is equal to 3. I know that f of 3 is equal to 3. Yeah? What does that mean? In fact, I can say that it's between, I know with certainty that it's not between, I can say with certainty it's actually on the open interval from 1 to 2, can't I? Yeah? Because it has to go from 0 to 5, therefore it must pass through 3. So some point on this interval hits 3, some point on this interval has a y value of 3. So that means that f of c is 3 and f of 3 is 3. And we have a nice differentiable function, a nice continuous function on the closed bounded interval 1 to 3. Rolle's theorem applies. So by Rolle's theorem, and it needs a new name, there is some point D in between C and 3, such that f prime of D is equal to 0. Yeah? So let's just walk through this one more time, okay? I know that f of x goes from 0 to 5 between 1 and 2, so it has to cross over y equals 3 because it's a continuous function, right? Let's call the point at which it does that c, x equals c. I know that f of 3 is also 3, so by Rolle's theorem, there's some point D between c and 3, such that f prime of D is 0. In our worst case scenario, let's draw our worst case scenario. Here's 1, 2, 3. F of 1 is 0, f of 2 is 5, f of 3 is 3. Ostensibly what we've done is said, well, there has to be one point between 1 and 2 where we hit this y value, right? And it looks like it might be here somewhere. Yeah? Maybe our curve is this thing. Yeah? So we found the point at which the y value matches, and with this point, we apply Rolle's theorem. And we know by Rolle's theorem that there's some point between, we call this point C, and x equals 3, such that we do have a horizontal tangent. Okay? Let's do another problem, or another example with the same problem, rather. Let me copy my table of values one more time. My table of values was, oops, there it is. One, two, three, 0, 5, 3, 1, 1, 4. Question, this is part B. Must f double prime of x equal to 0 have a solution in the interval from 1 to 3? Yeah? Pause the video, see what you think. So the answer here is yes. What do we want to do? We really want to apply Rolle's theorem to f prime. Yeah? We know that it's twice differentiable, which means that f prime of x is continuous, certainly on the closed bounded interval 1 to 3. Oops. And it's differentiable on the closed interval, so it's certainly differentiable on the open interval from 1 to 3. Yeah? And we know that f prime of 1 is equal to f prime of 2. So Rolle's theorem applies, right? So what does Rolle's theorem say? That means that there is some point C in the open interval between 1 and 2 where the derivative of f prime, which is f double prime, of C is equal to 0. Yeah? All right. So let's look at Rolle's theorem in a slightly different way. So let's think about it in a slightly different way. Here I have some point A, and here's B. And my two function values are, of course, the same to apply Rolle's theorem. And here's a nice differentiable function, maybe, on the closed interval AB. Another way of rephrasing Rolle's theorem is saying that, well, let's look at this. What's the slope of the secant line between the endpoints on my interval? Well, if f of b is equal to f of a, how do we compute slopes of secant lines? Let's remember, the slope of a secant line is f of b minus f of a over b minus a, right? That's the slope of a secant line. Well, if f of b is equal to f of a, what does that mean for us? It means that the slope of the secant line is 0, right? And so Rolle's theorem allowed us to conclude that there is some point at which the slope of the tangent line equals the slope of the secant line, or the instantaneous rate of change is equal to 0. Yeah? So let's generalize this. What we can do, rather than having it, let's remove the restriction that f of a is equal to f of b, and let's draw a slightly different picture with that same idea. AB. Suppose here's f of a, and maybe f of b is up here, and we're just going to tilt this prototype of a picture. Suppose I have a nice, easy function, a smooth differentiable function between the 2 points. Yeah? What we can conclude, if we tilt the picture and remove the restriction that the endpoints have the same y value, is that if you compute the slope of the secant line between the endpoints, there is some point in between, it looks like it's here, at which the slope of the tangent line is the same as the slope of the secant line between the endpoints. Yeah? And this is actually called the mean value theorem. It has almost the same conditions as Rolle's theorem, except we've removed one, right? Let f of x be continuous on the closed interval between a and b, closed bounded interval, and differentiable on the open interval from a to b. Yeah? So we're removing the restriction that f of a is equal to f of b. Then there is some value c. In my picture here, it looks like it's about here in the open interval AB, such that f prime of c is equal to f of b minus f of a over b minus a. Yeah? And indeed, that's what our picture said. The slope of the secant line, f of b minus f of a over b minus a, is equal to the slope of the tangent line at that special point c, which is f prime of c. Another way of reading this is that the average value of the function, yeah, the average, this is the, or the average, sorry, not average value of the function, the average rate of change is equal to the instantaneous rate of change of the function at some point. The average rate of change of the function on an interval is equal to the instantaneous rate of change at some point. And we'll see an example as to why that might be useful. And let's just verify for ourselves, if we reintroduce that condition that f of b is equal to f of a, what does the right-hand side of the mean value theorem become? It becomes 0, right? And you get Rolle's theorem. So the mean value theorem, we usually abbreviate it MVT, is a generalization of Rolle's theorem. Yeah? And in fact, you use Rolle's theorem to prove the mean value theorem. And the proof's in the book, or we can talk about it in office hours if you're interested in. But let's see an example. Let's revisit our familiar function that we saw. And it's the same function. F is twice differentiable. And it has the same table of values that we used before. One, two, three, 0, 5, 4, 1, 1, 4. Yeah? Oops, 0, 5, 3. Sorry about that. Question. Must f of x ever decrease in the closed bounded interval 1 to 3? Yeah? Pause the video, see what you think. So I know what you're thinking. Let's sketch a little picture, right? Pictures always help. Here's 1, 2, 3, 0, 5, 3. And you say, well, you know, might look something like this. And if it goes from 5 to 3, it has to decrease, right? But how do you know? How do you know that there's not some strange special case, right? Because the question is, must it? Not just the one picture that we drew, but must all such twice differentiable functions decrease somewhere between 1 and 3? How can we prove that? Well, let's use the idea that we just talked about. I know it goes from a y value of 5 to a y value of 3. And let's think about what's the average rate of change between those 2 points. Well, that red line there looks negative, right? So all that I have to do is let's compute the average rate of change, right? What is f of 3 minus f of 2 divided by 3 minus 2? It's equal to 3 minus 5 divided by 3 minus 2, which is negative 2, right? And that's negative. And if the mean value theorem applies, we know that the instantaneous rate of change, some point between 2 and 3, must therefore be -2. And we'll be done. So does the mean value theorem apply? Absolutely, because we have twice differentiability, right? So let's put this together. Because f of x is continuous on the closed interval between 1 and 3 and differentiable on the open interval from 1 to 3. There is some point c in the open interval from 1 to 3 such that f prime of c is equal to f of 3 minus f of 2 over 3 minus 2, which is -2, right? And this follows, of course, by the mean value theorem. By mean value theorem. So what does this allow us to conclude? Because the instantaneous rate of change is somewhere negative, it must therefore decrease, right? We must have a decreasing function. At least somewhere, at least at one point. Let's see another example. Suppose you pass a traffic camera, everybody's favorite, right? At 1:30 p.m. Yeah? You're driving on the highway, you pass a traffic camera. And suppose you pass another one. And it's 45 miles away. And you pass it at 2 o'clock. Yeah? The question is, suppose the companies who own the traffic cameras, should they send you a ticket? That doesn't look right. I think it's I before. I don't know. Anyway. This is a hard question here. Should you get a ticket? Yeah? Pause the video, see what you think. So we know that the statement of the mean value theorem says that if we have a continuous function on a closed bounded interval and a differentiable function on the open interval, then there is a point at which the average rate of change on the interval is the same as the instantaneous rate of change at some point. Yeah? There is a point at which they're the same. So let's begin. We need a function, right? So let f of t be your position on the road. And assume you don't start, teleporting everywhere, doing something weird. We can say that this is, or we can assume that this is a nice differentiable function, right? That's not an outrageous assumption in these types of problems. Let's assume that we have a nice differentiable position function. And let's let t equals 0 correspond to 1 o'clock or 1:30 p.m. And let's say that t equals 1/2 correspond to 2 o'clock p.m. This is p.m. Yeah? Before we begin, we need to define, I forgot to define, if we get a ticket, we need a speed limit, right? So suppose our speed limit, sorry about that, suppose the speed limit is 60 miles per hour. I apologize. Suppose our speed limit is 60 miles per hour. We pass a traffic light camera at 1:30 p.m. and another traffic light camera 45 miles away 30 minutes later. If the speed limit is 60 miles per hour, should we receive a ticket? So if in our position function, t of 0 corresponds to 1:30, t of 1/2 corresponds to 2 o'clock, what's the average velocity of our car? Well, the average rate of change is, of course, f of 1/2 minus f of 0 divided by 1/2 minus 0, right? Well, what's your position at 2 o'clock? You're 45 miles away. You've traveled 45 miles minus your initial position is 0 divided by 1/2 minus 0. And what is this? This is 90, isn't it? So what does this mean? This means that your average rate of change is 90 miles an hour. Your average velocity is 90 miles an hour. So we know by the mean value theorem, because we have a nice differentiable function, the mean value theorem applies, there is some times c in the open interval between 0 and 1/2, so between the traffic light cameras, such that your velocity at that time c is 90 miles per hour. So yes, you should get a ticket. And this is kind of powerful. You never need to be observed to have traveled 90 miles an hour for us to assert that you must have done it at least once. Yeah, and that's really kind of a cool feature. Yeah. All right, guys, so I hope that this helps. I'm going to post some homework in Canvas for you to work on. If you have any questions whatsoever, feel free to reach out via email, or we can set up a time to Zoom, and I look forward to all of your questions. Thanks so much for watching.